So today we will be implementing the k-nearest neighbors algorithm in Python. It won't be too complicated, but I'm going to start by drawing things out just to make it a little bit simpler. So let's get green here, and we're going to draw a basic graph. Label this x1, x2, and we're going to take some points and draw them. I'm going to take light green, mix in some light greens. Okay, so this represents our training data set, right? We have a parameter x1, a parameter x2, some graph, and then we have a classification either light blue or light green. So now we're going to represent our test data set, and we're going to make a classification for this point. And actually that's a bad point to choose, so let me just erase that. I'm going to make a classification for this point here using the k-nearest neighbors. So if we set k-nearest neighbors equal to 3, then we have 2 green points and 1 light blue point in the nearest neighbors kind of area, right? And so our majority vote would be 2 to 1, and that would mean that it's light green. So this would become light green. So that's our k-nearest neighbors algorithm that we're going to implement in Python. Coming back to Python and implementing the k-nearest neighbors algorithm, we're going to define a class, KNN classifier, and we're going to define init self let's take in x train and y train in place of a fit method, and what else will we do? We will set self dot x train equal to x train, self dot y train equal to y train, and we'll need to take in the nearest neighbors as well, and we'll set that by default equal to 3. And we're going to leave a note for ourselves to only take in num_np arrays. And that's a note for you too. Okay, so now we need some way to measure the distance between points. So we're going to do compute distance self, why not, and we'll do x1, x2. We want this to all be like vectorized essentially, so we're going to return np.sqrt, np.sum, and then we're going to do x1 minus x2 squared, define predict. So this is going to give us our predictions. We're going to take in self, we're going to take in x test, and we're going to return predictions. So here's where things get interesting. We're going to start with an empty list of predictions, and Then for X train item in X train, excuse me, for X test item in X test, we're going to loop through all of those, and for each one of those we're going to compute the distances between the X train dot append compute distance x1 x2 what's going on here? Compute distance. Oh, compute distance x1 x2. We're going to need to take in, oh, what is x1, x2? So X train item and X test item. So what have we done here? For each item in X test and for each item in X train, we are for each item in X test, excuse me, we're going through and taking the distance between that item in X test and all of the items in X train, and we're computing those distances and plugging them in. Clearly this is a brute force approach, but that's fine as long as it works. Now I'm going to cheat for a second and take a look at my notes. Okay, I'm back from cheating and looking at my notes, and the next thing we need to do is get the indices of the distances that are the nearest neighbors, if that makes sense. So indices is equal to np.argsort. This is going to return this essentially returns it's indirect sorting, specify that the kind, it returns the indices of the same shape that index the data along the given axis in sorted order. So what does that mean? Essentially we are returning the indices in the order that would sort the array if we were sorting the array, but we're not actually sorting the array. So that's a useful function right away. I would not want to implement that. That's its own video. So we're only going to take the indices from the first distance to the number of neighbors that we need. So now we want to capture the majority vote, right? So count dict equals for I in nearest neighbors count dict I. We're just using a dictionary here. It's probably better to use some other data structure, but this works. Dot count I. So taking the list of nearest neighbors. Why is this? Oh, right, I forgot. So we need to actually get the nearest neighbors. And set that equals self.y train indices. Okay, so that was simple enough. So now how do we implement the majority vote? We have a dictionary of all the counts and the classifications. So how do we actually implement the majority vote? Well, we need to find the mode of the dictionary. And the way we do that is values is equal to list count dict dot values. Keys is equal to list count dict dot keys. I'm sure you can see where I'm going with this. And now majority vote. I got this straight off of Stack Exchange. It's pretty good. Normally I would just use some sort of module for mode, but I'm restricting myself to NumPy, and they don't have a module for that. Values dot index max values. And predictions dot append majority vote. Okay. That ought to work. So that is our implementation in Python. It's quite simple, not too complex at all. Now we need to test it, and so I'm going to look at my notes again, and I'll come back when I'm ready to test it. Okay, so to test this, we're going to use scikit-learn, pandas, and the iris dataset, which is a pretty famous dataset. I'll put a link to it in the description. So from sklearn.metrics, import classification report, import pandas as PD, from sklearn.model selection, import train test split. And what are we looking for with this? We are looking to get the classification score in like the 90% right. So a 90% accuracy, and that I think will validate what we've done so far. And now I'm just pulling the data from my home directory and iris.columns. We're going to rename the columns. Now there are 4 columns in our data set, which are just measurements of different lengths of different parts of the anatomy of a flower. And the 5th column is the classification of the flower. So we're just going to keep things really simple and name these 1, 2, 3, 4, 4, 5. Actually, we'll name the 5th one class. And this is not how this works. Iris.columns equals that. Okay. So now we want xtrain, xtest, ytrain, ytest equal to train underscore test underscore split iris, and go ahead and use this nice kind of syntactic sugar type thing to get just the training data that we need. Oops, one extra. Now iris and class. Okay, so train test split. What this does is it splits our data into training and testing, probably with either 70%, 30%, or 80%, 26% split. I'm not sure which, but you can definitely set that. Either one is fine for my purposes, so I'm just going to leave it. Now we're going to go CLF is equal to KNN classifier and we're going to put in x train dot to numpy. I'm going to get rid of the whole pandas data frame. Y train dot to numpy. Oops. And predictions is equal to clf dot predict. Oops. Predict. If I can type it. X test dot to underscore numpy. Print classification underscore report y test dot to numpy comma np dot array predictions. Okay, so this is not the best way to implement this, but I've done it. I have successfully implemented a little test. So let's give this a shot and see what happens. Failed to load iris data. Okay, that's because it's not called iris data. It's called iris.data. Okay, and we get a classification report. So, as you can see, it is with 3 nearest neighbors, successfully predicting 100% of iris setosa, 100% of iris versicolor, and 85% of iris virginica for a total accuracy of 0.95. Now that's pretty good. Let's see what happens when we change it to 5 nearest neighbors, maybe. Now, where do I do that? Okay, the accuracy goes up to 97% accuracy, so that's excellent. So I'd say this is the end of this video. We've successfully implemented the k-nearest neighbors algorithm, and with 97% accuracy. So that's it for this video. Thank you.